Thank you so much. Thank you for having me today, and thank you for everyone that's joining this talk. So the research I'm going to present today is part of the research that Rachel Stubbington and Judy England have started a few, like 8 years ago. It's a collaboration between the Nottingham Trent University and the Environment Agency. And so we're going to talk about chalk rivers, and I guess most of you know what they are and why they're important. But just a little reminder, they are very interesting ecosystems that harbor a very big biodiversity. They have this perennial clear water section, so flowing all the time, but also this winterborne very typical streams that dry for part of the year. And my group does a lot of research on this winterborne. But today I'm going to talk about the chalk stream in general, and I'm going to talk a lot about drying, which happen in winterborne. But yeah, it's chalk streams in general that go from the south to the east of England, as you can see on this map. And so in this winterborne and in this chalk stream, you have a unique biodiversity, including some rare and nationally scarce species, such as this mayfly and this Plecoptera. And we also know that these chalk streams are in the center of the attention. People love them, people want to protect them, and there are more and more problems with, for example, water abstraction, but also pollution and drying, which is what I'm going to talk mostly today about. And so I say the word drying and drought, and these are two different terms. Drying can happen at any time in any years. So, for example, here you have the calm catchment, and during no drought years, you'll have some sections of the rivers that will dry, mainly headwaters. So they are the winterboards. But a drought is an extreme event, high temperature for a long time, no rain, which leads the stream to dry for longer length. And this might affect the stream locally. So you'll have earlier and longer drying event in the winterborne, severe drying. So it's going to get more dry, so species will have a harder time to survive, and you might have more frequent drying events. And in the perennial sections, you'll have low flows, which might be a problem for some aquatic invertebrates. And also regionally, drought will change the spatial configuration of where drying happens, and places that don't dry usually might dry in these years. And this will affect the invertebrate community resilience and resistance capacity. So I'm going to try to explain what I mean by resistance and resilience. So in a river network, we have a lot of communities in different sections. Some might be more resistant and more resilient than others. So here in orange, there is a drought, and you see this orange community doesn't really change. If we talk, for example, about diversity, the biodiversity won't go lower during a drought. It's a resistant community. And usually communities will, the ones that are not resistant, will recover with some time given to them. So this is the resilience. And but if droughts become more severe, more long, you might reach that point where community won't recover anymore. And that's a bit what we're trying to study, understand at which point do we reach this tipping point at the river network scale. And so why drought is a problem? I mean, you've seen this past year has been the most rainy in a very long time, but there has been drier years in the recent past. There is no obvious evidence that droughts are becoming more frequent or more severe, but they're predicted to become more frequent and more severe. So you can see here, for example, predictions for England's drought frequency will increase. So we will have more dry years in the future. And so, yeah, now after this introduction, I'm going to tell you what we have learned from our research about the effects of drying and drought in chalk rivers. And we've been focusing a lot of our research on the Colne and Lee catchment that you probably all know there. So the Colne and Lee catchment includes intermittent sections, so temporary rivers. They flow not all the time, they dry for part of the time, and also perennial sections. And one of the most amazing data that we have from this river catchment is this flow state of observation. So the Environment Agency has been going for years, since 1997, every month across the river network and taking note of if the river was flowing, if the river was ponded, if the river was dry. And we can see how, so the percentage on the side is the amount of the river network that is dry. And so you can see that it varies across years, and you can clearly see what happened during the drought years. So for example, late 90s, 2005-06, 2012, and then a bit in the past few years, 2018 and 2019 were quite dry years. So this data is very interesting because we can know what's happening at the whole network scale. And so I'll present some of our research here. First thing we found was that the flow permanence at a site, so how often does it dry or how often does it flow, really impact the richness of species we will find. So the richness is the number of species you will find. So as a section flows more, you'll find more species. And also, the distance to perennial ridge is important. So if you have a perennial section close by, you'll have invertebrate recolonizing aerially, probably, which will increase the richness. So the impact of drying depends on local conditions, so the drying duration at the site, but also the regional configuration of the drying. Then we looked at the recovery of the communities, and we used this index, which is called daily. It's kind of a drought impact index. So the lower the value, the most drought impacted a community. And what we found is that after a drought or no flow event, community take on average 3 years to come back to a normal state, so normal daily, a daily which is indicative of non-drought conditions. So, which means approximately most community takes on average 3 years to recover. And the figure next to it shows each point is a community, and you can see during drought years, the composition of the community will change from what it is on average, and then it will take some time for it to come back within what they are usually. And also we found that some taxa may take up to 10 years to return post-drought. So what does this mean is that if we have more frequent years, more frequent droughts, if they happen like more than every 3 years or less than every 3 years, then we might have a partial recovery. And we also looked at species extinction risks. So when do invertebrates reach this point where they might go extinct locally? So we looked at the river network scale, and at which point do we see a huge decline in the occurrence of some species. And what we found is that after 3 years with dry condition covering more than 50% of the network, we saw a huge increase in the extinction risk of some species, and mainly the most high flow adapted one. So Dry condition covering 50% of the network for 3 years is a lot. It's not, it hasn't happened yet, but maybe in the future. So more extent, a larger extent of drying might increase extinction risk. So this is, so yeah, we did this research first, and then we thought, but we're missing a big part of the picture. What happens in these systems when they're impacted by other human activities? So because we looked only at the effect of drying. So then we decided to add the interaction with human stresses. And what does it mean? Are community more sensitive to drought if they are under high pollution, or are they more resilient? Because anyway, they're already screwed. So do they mind about drought? And so we looked at the impact of different human activities such as land use, water abstraction, and water pollution. And what we're expecting is that higher impact means more risk of decreasing resilience and more risk of crossing this threshold where community shift to something else. So we used microinvertebrate data from the whole of the chalk stream area, so from the south of England to the east, which included human impacting formation, which include flow condition, flow alteration, so is it abstracted or not, water temperature, and also morphological alteration, water quality. So a lot of different human impacts. And we looked at how these impacts interacted with drought. And so we had all these sites across the chalk area. And this is to show you the droughts that have happened. It's kind of the same as I showed before for the Colne and Lee River. And what we found is that invertebrate richness respond negatively to drought at sites with low water quality. So what we here, low flow anomaly, it's on this side of the graph, you have the very low flow here, the very high flow. And what we see is that under low water quality in red, the richness is very low, whereas it's very high. There is a high difference. Whereas when you go at very high flow, things are kind of mixed together. And same, we looked at the recovery of the community after the drought. So this is the time since drought in years. And we saw that under natural flow condition, you have a steady increase in richness. So it's the middle one here. Under water abstraction, you'll have no recovery, and under water addition, which can happen sometimes, you'll have a much faster recovery. So water use can also impact the recovery of the communities post-drought. So yeah, this was a bit of a snippet of all our different research. And in conclusion, what we've learned is that invertebrate communities are quite resilient to drought so far. They recover usually within 3 years, but increasing drought duration, frequency, and extent might have a negative effect on these communities in the future. And low water quality and water abstraction can enhance the impact of drought on community. And what we're trying to do now is to better understand at which point do we reach a threshold? What is a threshold? When do we lose most of the taxa? So yeah, we're looking at these shifts in community composition and also going to predict future invertebrate communities. And that's it for me.
Thank you.
Thanks.